So, hello everybody. My name is Tommi Mäkilä, and I'm here with my colleague Jukka Taimisto to speak a little about Bluetooth fuzzing and why you should actually bother doing it. A slight overview of the talk. We will first go through some test results, and also after that look a little bit into the anomalies that actually work against different types of devices, and then discuss why they actually work. And then there's a small portion of actual Bluetooth security measures used in different devices, and then the wrap up. So a little bit about us. We don't actually do exploits, we make fuzzers, so our primary concern is to crash software. And once we actually manage to crash it, our job is pretty much done at that point. Of course, along the way we do find situations where exploits could be easily made, because it's not very hard to actually write exploits if the target resembles something like a Swiss cheese. Okay, so we've been basically doing this for 5 years now. We have attended the Bluetooth Special Interest Group's Plugfests, which is like an industry standard interop testing event. It's held like 3 times a year. So we've been going there steadily since 2006 to do some fuzz testing. And the sad thing is that while we have been doing it for such a long time, we haven't seen any improvements happening there. So the protocol robustness has not increased during the years. So I don't know if you can actually see this, but here are some anonymous results from many of the UPF events that we have been attending. So the green bars basically indicate the amount of test runs we have managed to run in each event. So it's usually like something between 30 to 50 different test runs on different Bluetooth profiles and protocols. And out of those, the red bars actually show the failed ones. So the amount of failed test runs per event is relatively high. I think the best one we have actually achieved is something like 51%, and the worst is way over 90. And this basically consists of all kinds of devices, because it's like a testing event when every vendor comes in to test their devices against each other.
Yeah, well, the UPF events usually, sorry.
Can I have a quick question about this graph?
Yep.
Can you clarify, surely you don't mean a test case by a test run, so you mean what? One device does it with a test suite is what's one test run?
One test run is actually because we have fuzzers for different Bluetooth profiles and protocols. So one test run indicates one testing session with one protocol or profile.
And then failed means what? And there was at least one crash?
Yeah, the fail is actually outright crash, because what we indicate as fail is something that the device actually cannot answer to you anymore, or does a reboot outright or something like that. So that's the fail verdict.
Yeah, well, the UPF events usually have devices which are in development or are prototypes. We wanted to see if the current situation is any better. So we did last spring this car kit testing bonanza, where we took 15 different car kits. 6 of those were in-car car kits pre-installed on the cars, and then 9 were aftermarket car kits which you can buy. We found problems with 13 of the car kits, and there were 2 car kits which had such a complex logic that we couldn't get any meaningful results. We couldn't get any reproducible way to test them. Some in-car car kits crashed so bad that we actually had to send the car back to dealership for fixing the problem. And at least on one car we crashed the total infotainment system. You could not use the radio or play CD or do anything with it. We didn't crash the actual logic which controls motors or such. That was accessible still, but the infotainment system and navigation was completely shut down. 10 of those car kits actually crashed with L2CAP, which is the lowest protocol layer we test. And that didn't require any pairing. So once we were able to establish a L2CAP connection, we were able to crash 10 of those. And we also tested HFP and A2DP profiles. HFP is used for hands-free, and A2DP is used for media streaming. So those are the most commonly available profiles on car kits. So the kind of testing that we do is fuzzing. I'm pretty sure everyone here is already aware of what fuzzing is. But basically, it's just sending anomalies data or invalid data in large amounts to a device. And in our case, we use a system called intelligent fuzzing, where we actually kind of design the data that we send, but it seems that random fuzzing is also quite effective. And usually, the kind of failures we see are crashes, because it's pretty hard to instrument an hands-free device. We do completely black box testing. We do not have any instrumentation in the headset. We just see that it doesn't work anymore after we have sent some cases. For Bluetooth, we test every protocol or profile from L2CAP above. That's because those profiles are usually implemented in the host stack, and they are implemented in software, whereas the controller stack, the link manager protocol and link controller, they are usually done in hardware, and we don't want to use any extra hardware. We want to use just basic Bluetooth dongle to send the data. We use a model-based fuzzing, where we actually make a model of the protocol or profile we are testing, and then we design the anomalies to fit fields in the protocol. For example, if the profile has a length field, we design anomalies such that they fit the length field. 32-bit length field we put zeros or FFs or something like that. And for ASCII fields, we put ASCII in it. So we don't do random testing. We try to actually design the test cases so that they will work better. There are about 25 profiles currently for which we have tools. And for profile, we have something like at least 10,000 test cases for every profile. But for example, to L2CAP, the full test run is 90,000 cases. And you can go beyond that if you want to. And no special hardware is used. We just use a Bluetooth dongle to send the data.
Okay. So during our testing sessions, we have actually managed to narrow down certain anomaly types that seem to work against a multitude of devices. And these are actually real-life examples that we have used to crash some devices. We don't, of course, enclose the exact devices that we crashed, but still. So the first anomaly type is a simple length field. This is actually a really simple anomaly. We just basically lie the length of the message that is being sent. So we might put there that there isn't any data coming in, or we might lie that there's the maximum amount of data coming in, while we are still just including the basic frame of the protocol. This seemed to be particularly effective when applied to TLV structures, where you have a type and length and value. But I will talk a bit more about TLV a bit later on. So I don't know if you can see anything of the examples, but I will go through them. So on the left side, you will see just a very simple L2CAP connect request used to connect to the service discovery protocol service. So it's a very simple protocol frame. And what actually works is just replace the initial length field, which indicates the length of the whole packet. Just replace it with FFs. And this is unfortunately, this is a quite common failure mode in Bluetooth devices. So just put an initial length and the device crashes. Because obviously it's waiting for a lot of more data to come in, but it just cannot handle it anymore. And to apply the same to TLV length, here we have an A2DP set configuration message that is used to pretty much just set the values for a data audio stream. So you just define all settings like the sampling rate and stuff like that. So here we do it does have a TLV structure, and we lie about the TLV, which is a media codec TLV. And we say that there's no data coming in, but we do include the data. But we get a crash. Okay, then a bit more about TLV. Basically, TLV structures are really hard to parse because you might not have any preset order when they might come in. You just basically have to parse the whole payload because you want to search for a specific TLV, and you just have to go through all of them. So you cannot expect, most of the time you just cannot expect that, okay, the first TLV is this and the second is this. Once we actually start messing the structure up in the TLVs, the targets usually go totally bonkers because they just cannot handle the data coming in because they totally lost their sense of place actually when you start fuzzing the TLV. So they don't know anymore where the TLV structure is going. And of course you can apply multi-field anomalies to this. So this basically just fuzz two different fields. You can fuzz like a type and length field at the same time. But I have a better example of that a bit later on. So here's an example. This is an OBEX object push connect message. OBEX in itself is a quite odd protocol because it actually uses it has two means to verify the amount of data in a TLV structure. It has both the length and it has a null terminator in the payload in many of the headers. So you have kind of two ways to, that you have to check that the data is there. So what we do here is we just basically we calculate the length correctly, but we just basically send a lot of null terminators in the payload. And this seems to be a very common fail in Bluetooth devices as well because they just can't handle the null amount of nulls in there for some reason. We have not of course gone very too deep into the code section because we do black box texting basically, so we don't know what exactly causes this, but anyway. Okay, then we have the good old data structure fuzzing, which basically means just inserting too much or too little data in a protocol frame. And sadly, it just seems that, like the previous speaker was saying, that if you do a buffer overflow with straight A's and nothing else, then it's bad. But it seems to be very effective in Bluetooth. And there's actually an example of that. So this is the initial message used in hands-free when you're setting up a connection with the hands-free device. So you just basically exchange the supported features between devices. And you're supposed to have a numeric value in the command. So what we do is just completely erase that numeric value and insert a lot of uppercase and lowercase a's there. And this one actually comes with a funny story, or sad if you wish. There was this vendor testing with us at one of the UPS a couple of years back. So they had a hands-free unique device, and we were sending in this particular test case, and the device crashed. And we had a little discussion with them, the usual, you cannot do this type of thing because that's the mindset. And then they suddenly just left. But they came back the next day. And apparently they had fixed their problem, and they wanted to do a retest with us. So of course we do that. So we did the test case and it passed. But then we proceeded to the next test case, which is actually identical to that, but all the A's are uppercase. and the device crashed again. So apparently what they had done was that they had made a filter that filtered in the string of upper and lowercase a's, and when we sent in the uppercase a's only, it crashed again. I don't know the end of that story, but I hope they actually started thinking the situation a bit more after that. Then we have repeats. This is actually a bit different because it contains only valid data. But what we do is that we just repeat certain elements within a frame many, many times. And these usually cause all kinds of strange situations where the device actually starts acting really slow. You cannot access the UE anymore, and so on. So here's a typical example of that. It's again a A2 DPSet configuration message, which has a mandatory media transport TLV that doesn't have any value actually by default. So what we actually do is we just take that one TLV block and we repeat it around 1,000 times or so within the one frame. So what probably happens here is that the system under test just starts parsing the TLV elements over and over and over again. And eventually it just runs out of resources. And everything starts acting really slow until eventually it will totally crash. Okay, so this is a fairly recent discovery that we have seen with some devices, is that you don't basically have to fuzz at all. You can just send like a huge block of valid data into the Bluetooth, and some chipsets seem to be actually just stopping after that, and resulting in a situation where you just have to do a hardware reset. This is particularly present in devices that by nature have less resources than others, so just like headsets and so on. But it's hard to say how usual this problem is, because we have seen a couple of devices that do this, but it's not very widespread, hopefully. But if it's actually, if the problem is in the stack, if it's in the stack, it's going to spread like a wildfire, because there are not that many stack vendors that people use. So if it's down in the stack, then. And one thing about this is that this really doesn't need any anomalies. You can just send valid data, a huge block out of it. And then one odd thing is that many Bluetooth implementations actually they're quite cluttered, because you might have different vendors working on one device. So there might be one vendor doing one profile and another vendor doing another profile. So what we have actually seen that these profiles, even though many of them use the same components like AT commands, and OBEX uses, of course, OBEX commands, it seems that some of these component profiles that have been implemented actually implement their own AT parsers. They don't use some common provided AT parser in the stack, but they implement their own. And this results in a situation where we have seen that doing a specific type of anomaly against a device against a specific profile might not actually work on the same device against another profile. So it's a clear indication that the current situation is that if you want to test it properly, you have to go through all the profiles, because they apparently are using a lot of different components, even though there would be like a common interface available. One example was actually one car we tested last spring. It not only did have one different parsers, it actually had two different Bluetooth radios in it, handling two different things. So you had a hands-free profile running on the car, and you had an audio streaming profile on the car. And they were made by different vendors, and the car actually had two Bluetooth radios and two different Bluetooth stacks. So, what could we do in the future? We have tried many of these. Given that Bluetooth implementation in general start acting a bit better, and we cannot crash them with the simplest ones, we of course could do a much more complicated anomalies. Of course, there's a multi-field meaning that we just basically fuzz different fields in the protocol frame at the same time. Then there's sequence anomalies, which are basically meant to attack state machines instead of parsers. So you might have a static or variable message sequence to do certain things in Bluetooth. So what we could do is just actually switch the messages in that. Just send something totally unexpected in the state the target is in. Then, of course, multi-profile. Bluetooth does many things using different profiles at once. You might have like a car kit doing a hands-free and a phone book access at the same time. So one option is to actually fuzz different profiles at once or so. And since Bluetooth is constantly evolving technology, they come up with new stuff all the time. The recent big improvement is Bluetooth Low Energy, which is basically using a completely new radio and all that. It's used to control like sensor equipment and using as little as power as possible. So it's going to bring up much more, make the Bluetooth in general much more complex, and hence we think that there probably is going to be a lot of vulnerabilities over there. Concerning that, even the classic Bluetooth, it took like many years until they actually managed to get L2 cap in a condition that different devices didn't just spontaneously reboot, even though they didn't try to do any fuzzing. So here's one example of the multi-field anomaly. Of course, the problem with this is that if you want to actually catch the problem, if you want to go through your code and find what's wrong in there, then fuzzing different fields at once can make that much more harder, because you don't have the exact cause in hand. So this is basically the same example I was showing earlier with the OPP, but in this case we are just using the null terminators in the value, plus we are using a unknown header tag in the TLV. So we have seen that one device actually, it was able to handle, if we fuzzed the tag field, we inserted the unknown header there, it was able to parse that. And then we tried the value with a lot of null terminators, and it was able to parse that. But once we actually started fuzzing the DAG field and the value field, the device crashed. So one reason for this might be that it actually has some predefined ways to actually handle different TLV types. So once it got an unknown header tag, it had no idea what to do with the payload, and did a crash. It seems to be a very common way to handle errors in Bluetooth, just crash, and not try to do anything fancy with it, or return an error or something, just crash. And then the sequence anomalies, so it's basically just rearranging the messages in a valid sequence. So you might do a connect, and then if you do like try audio streaming, you might do a connect and then try to open the audio stream immediately without doing the necessary audio stream configuration first and things like that. Of course, this proves much more efficient with profiles and protocols that have complex sequences and complex state machines, because it's usually if there's a lot of states in the machine, it can get easily confused in what state it is in. And this is usually done with perfectly normal valid messages, but of course you could start analyzing even that, and for some additional fun. Multi-profile. One example of multi-profile is to just basically fuzz different profiles at once. But there's another catch in it, because especially when you're doing testing client-side devices. Client-side devices, testing them is pretty hard usually because it usually contains a lot of user interaction. You need to perform a certain operation in the device to actually trigger something so that we can return a fast message back to it. But we have found some useful ways to actually automate that, because when the multi-profile actually comes in, there are some certain cases in Bluetooth that do allow opening up some automatic attack vectors, such as using AVRCP, which is pretty much like a remote control profile used to remotely control audio devices and such. You can use that to trigger audio streams. So you can pretty much just say, okay, I want to play something, and the device just opens the stream A2DP to your, at which point you already have a new open attack vector. Another example is hands-free and the phone book access profile. So there are certain use cases where you might just basically indicate that, okay, with hands-free, that, okay, we have an incoming call from this number. And some car kits are actually able to do it, that they get the call in and they check the number, and then they start doing phone book access to check whose number is it. Yep.
Now a few ideas that we have gathered from the UPFs when talking to developers about why these type of anomalies work so well. It's actually very common response when we show the anomaly, when we show the case that we have sent, that the designer answers back that you cannot do that. The specification doesn't allow you to do that. In the Bluetooth world, they do a lot of interrupt testing. They have the UPFs 3 times a year, and every Bluetooth device has to pass through an interrupt testing. But they don't do any negative testing. The mindset is not there. A lot of people have no idea about fuzzing or about negative testing, even though it's been the talk of the year for 10 years or so. So a lot of people still haven't got a clue or are thinking in the old ways where you cannot send anything invalid, that you have a connection and every device is interrupt tested, and they just don't do that. So that is definitely one of the reasons why they don't even think about receiving 100 A's. And another reason is, of course, so what? So what if I make a $5 or €5 headset? So what if it breaks down when you send invalid data? It's not going to be a big problem. Well, that's true. It's not valid for that, but once you start to do things in that mindset, you don't even care about these things, and now you have all of a sudden Bluetooth in medical devices. And I really would like to know that the developers have not been thinking that, so what if it breaks, so what if it crashes, it just reboots. And of course, it's not easy. It's hard to actually implement an profile or a protocol, even if you try to think about security, even if you try to think about invalid messages. I have written my share of protocols and profiles, and Tommi has been able to break every one of them, at least once. Every time I have coded something, we actually did a bet when I did an HFP, which is pretty simple, 80 commands, and we agreed that if he cannot break anything, he will buy me a beer, and I promised to buy him a beer if he breaks, and it didn't take much. So it's sad. And then you combine this with ambiguous specifications and tight schedule when you are hurried to push something out. It's actually a wonder that devices actually work that well that they do. So especially the example with the OBEX was a good one, where there is a null terminator in the string and there is a length field in the TLV structure, but the specification doesn't say which one is right. What to do when the length and the null terminators do not match. So that's one of the examples of the ambiguous specifications.
Okay, a little bit about Bluetooth security measures. This is quite common stuff, but pairing is the most common way to protect Bluetooth devices, of course. You have two different types, basically. The legacy pairing, which is the old method of doing it. It's Bluetooth 2.0 and older. It uses, usually it uses like a 4-digit PIN code. You can insert a 16-digit PIN code, but I've very hardly seen any devices that use more than 4. Bluetooth 2.1 introduced something called simple secure pairing, which fixes a lot of problems with the old legacy pairing thing. But still, there's one critical aspect. Bluetooth by nature, it always leaves one attack vector open, even though you had pairing on. That's L2 cap. You can pretty much always, if you know a Bluetooth device address, you can always connect with L2 cap to the SDP PSM. PSM is like a equivalent of the port number in TCP. So this is a usability requirement, so you need to be able to scan the device what it can offer. And that's why they actually leave it open. And it's also a bit of a mindset thing. They have never thought that it would be an efficient attack vector, so because you don't have any negative stuff coming in. It's clearly specified that you should send this and this. And then the holy grail, evading pairing. Of course, we don't have any sure-shot way to do it, but there are some things that work every now and then. Social engineering is, of course, one that could be a whole different talk in itself. But I can imagine if you are sitting in an airport lounge and suddenly the airport lounge wants to pair with you, there would be many people that would accept that. One method is actually evading the whole improved secure simple pairing, and that can be simply done by saying that you're an old device. I'm a Bluetooth 2.0 device, at which point, because Bluetooth 2.1, for example, has to be backward compatible, it will go back to the legacy pairing at that point. So you can just completely evade all the improvements like that. Then there's this pairing mode introduced in secure simple pairing, which is basically meant for pairing with the device that doesn't have any way of inputting or any way of displaying data. So it's called just works, and it just works. So basically what you do, you initiate pairing and that's it. This is actually supposed to be used from a host device to a client device, but in some cases we have seen that you can reverse that process. You can just say, okay, I'm a headset, I want to pair with your phone. It just works and it goes through. And suddenly you're paired, and suddenly you have all the interfaces, all the services open. Of course, with legacy pairing, it's almost always the PIN codes are 4 zeros or 1, 2, 3, 4. People are too lazy to actually go through changing them. They use the defaults. Headsets usually have a hard-coded PIN code. You cannot even change that. And one thing we have discovered that once you start sending anomalies to the L2 cap layer, to the SDP PSM, which is always open, we have seen some devices actually lose completely their ability to pair. So they don't actually request any pairing after some anomalies.
Then there are, of course, other security measures that are deployed in devices and computers and phones. Most common one is the non-discoverable mode. Almost every phone nowadays, it's not discoverable by default. You have to enable it, and then it's discoverable for 2 minutes or so. But you have to remember that even if it's not discoverable, it still may accept connections. Many devices are not shown in scan, but you still can do SDP query for it, which means, of course, that you can connect to L2 cap. Then there are dedicated pairing mode. Mostly every headset nowadays, you have to put it to a pairing mode where it will accept connections from everywhere, and then if it's not in pairing mode, then it will accept connections only from trusted devices, only from devices that you have paired with. And then this seems to be the new trick. is that the device actually, before accepting a connection, it does an SDP query back and checks what you are supporting and then enables those services. So you have to run an SDP server on your own, and that's not a problem for devices, of course, because they need to have the SDP. But for us, it was one obstacle we had to go through. So we have to have a SDP server running, and then we have to serve the correct service records for the device to enable its services so that we can connect and test them. And I think Windows 7 does this too. So it actually loads all the drivers after it looks at your devices, what profiles you are using. And then there are quite imaginative ways that, for example, car kit vendors have made the devices that you have to jump through certain hoops to even get your phone connected to a car. And it was also one of the reasons why there were 2 car kits that we couldn't interop with properly, because we would have needed to run a number of profiles. It didn't do anything unless it connected to PBAP and HFP and A2DP and before it actually talked any of those. But these kind of tricks, they make it a bit harder for a legitimate use. It took quite a number of clicks to actually get your phone paired to your car nowadays. And of course, when you are implementing a devices like that or security measures like that, you have to make sure that all the profiles use the same mechanisms. Because in Bluetooth world, a lot of the profiles are bought from different vendors, and now you have to make sure that all those profiles use the same security measures. There was actually one case where you could download an application to your phone which turned on the JustWorks pairing on the phone. So before downloading the application, it didn't accept JustWorks pairing, but after downloading the application, it accepted JustWorks for every profile. So it seems to be that the focus making Bluetooth devices secure has been on preventing the unauthorized access. So that is the line of defense, that if you have allowed the access to your phone and then somebody steals your diaries, it's your fault. So that seems to be the only defense. The underlying implementations are still crap. We still crash them once we get through the pairing phase. And unfortunately, it seems that that situation, that mindset is not changing. We actually have one of the major operating systems nowadays, we can still crash it with single RFCOM packet. But since it requires pairing, they didn't care that much when we told them about it. So we would like to see that people implementing Bluetooth devices spend some time actually doing some quality testing, of course with our tools, to make their implementations more robust. We have quite a lot of experience in testing various IP implementations, and from there we have seen that sometimes when you test one device at the border of the network or somewhere else, the anomalies actually propagate quite deep into the network. Like when we have been testing WLAN APs, we sometimes see anomalous data going into the authentication server, which is quite far away from the AP itself, and it's already in the network, deep inside the network. So we were thinking that maybe you could apply this to a Bluetooth. For example, you have a car kit integrated into your car, and it's integrated into the system which controls the brakes and allows you to tweak your car system. So how well are those defended? Are they completely separate, or are they running on the same processor, or do they share some buses and things like that? That would be an interesting thing to actually look further into. And finally, it's just not about security. Think about the case where you buy that €5 headset and the headset suddenly crashes or decides to do something funky and sends one invalid packet of data to your phone, and your phone crashes. So this is not only a security problem. I think that it's a problem in a valid use. When you have a lot of devices, different devices, and when one of them fails and sends invalid data, and then it crashes your system. So maybe that is also one thing that they need to be thinking about. Nowadays, we have medical devices, we have insulin pumps, which are controlled using Bluetooth devices. So the idea of actually injecting insulin through an anomaly is quite scary. And for headsets, headsets are something that people at our offices don't turn on anymore. Because once they crash, there is no way to reboot them. You have to tear them apart to take out the battery. And we have killed a lot of those. Yep. With that, I thank you, and if you have any questions, feel free to ask.